Track loads, temporary crossings. On the left, as you could see, we have track load and analysis, gas, or it could be liquid. On the right is the ArcGIS program where the location is. And it's just a matter of putting a location here. Okay. And now we have it saved. And I'll save this location here. And we're ready to go. Let's talk about the track load program, which was designed to calculate the overburden and track loads on a buried pipe with a single layer, basically soil only. The information used to design the program was taken from Newmark's integration of the Boussinesq equation, which is the key equation for track loads. And this was also from the work of M.G. Spangler on overburden and vehicle loads on the pipe. And then prior to that, Gas Research Institute, or GTI as they're known today, resulted from the API 1102 calculation back in 1991. So you can see all this is tied together. And then, of course, Patel, who was involved in this, conducted an effort to evaluate the work done by Spangler and the effects of stresses on pipelines. This analysis does not consider cyclic loading such as 1102 calculations, because this is a temporary calculation versus a permanent one, which would be 1102. The overburden is considered soil-only load. As the evaluation effort was undertaken, the first estimate of soil load on a pipe was that of the pipe supported by the entire weight of the overburden. Well, that's pretty conservative. So Spangler developed a load coefficient that predicted how much the overburden is carried by the pipe. This load coefficient is a function of the burial depth, which is part of the parameters that we input, trench width, and a friction coefficient between the backfill soil and the pipe trench walls. And that's a default in the calculations. This served to reduce the load on the pipe itself and allowing the surrounding soil to support a portion of the overburden. And of course, overburden, and you'll see in the program, is a function of the following parameters: the weight per unit volume of backfill, trench width, load coefficient, burial depth, friction coefficient between the backfill and trench. And also we have other parameters that include the crossing construction, such as being open cut, bored, or so on, soil type, such as clay, sand, and gravel, bending and deflection coefficients, a function of the construction type, and also impact factor, which is normally 1.5 for soil. And of course, temporary track load crossings are designed by considering the track to be a uniformly distributed surface as compared to a wheel load, which is a concentrated load, and estimating the soil load on the pipe using the same Boussinesq equation that Spangler applied at the crown for the point loading of the surface. Now back over here to the program itself, we talked about what we have is the track load and the ArcGIS. I put two different dots in here. I have one for a copy and one for the original. And this is the nice thing about it. It's point and click technology. So this is why I showed the program to begin with, so you have an idea where you're located. This is located near an interstate highway, and it just so happens this right of way seems to be used by others. You can see the tracks running down the right of way. That's not a good thing. And so this is one of the reasons there was some additional studies done here, because not only wheeled vehicles coming down, there was also track load. The other thing we need to consider is how do we get to this information here? And of course, we could easily bring it in by our hierarchy. And I'm going to bring in this particular line. And I'm going to do pipe crossings. And then I'm going to do some stress calculations just to show you what's in store for you. So let's talk about go back to the track load again. So we have custom pipe 24-inch 406 52,000 yield. We also have consideration for, you're not going to believe it, reduced wall thickness. And we could also turn this on up here if we wanted to. And we could also bring in the R-string calculations. We'll consider this a little bit later. But I just want to show, or you can manually put the metal loss in there. So you have two choices on that. I'm going to come back to that a little bit later. I'm going to shut this off a second. We'll come back. But this is the nice thing. If you have already done any investigative digs, you could easily bring in the integrated data to this location. We talked about the soil type, open cut, class 1, and this is where you could change things, and it'll change your parameters down here. This is a 1200 psi pipe, 3 foot of cover. Trench width is about 30 inches. The operating weight of the vehicle, in this case, it came from Ritchie Specs. It happened to be a bulldozer, 75,000 pounds. The width of the track chute was 16 inches, and the length of the track on the ground was 18 feet. This is where we changed the class locations. We got the friction coefficient, the soil, the weight of the backfill, the impact factor, which I talked about, is 1.5 for soil, and your bending coefficients and deflection coefficients. Also, that are part of the equations for the resistance. We also have the bending stress calculations. So if I wanted to select 50 foot and wanted to run a calculation for 1/10 of an inch, that'll be part of the calculation results. We also have interpolation method. We could include that if you want to be more exact at certain depths. We could calculate, and it looks like we included that. Yes, I did. I included it. Let's uncheck the box, and let's run it again. So we're below the maximum combined stress. So you could see with the reduced wall thickness, I'm going to produce a report just to show you the differences. And the nice thing about the report, it'll show you the data that the parameters that you inputted, both the pipe and operational data, the installation site characteristics, and the loading parameters. And then here, this is where we're considering full wall thickness. And of course it passed. So if we come back up here again, and now I'm going to consider metal loss. And I'm going to use one of these. See if I have another one. There we go. I'm going to select this one. This is a little bit less stringent, but it's stringent. And you could see if I check the box again and then rerun the calculations as I did just before, it's above the maximum combined stress. We run that same report again, and what we're going to see is a big red flag, and it's significant. It just so happens that they did fix that anomaly. It was repaired with a composite sleeve. So we could come back to the first report and say we could put the results in here. And this is the nice thing about this. Oh, opening up too many things at the same time. And I could come up here to the top. And we could say repair with composite sleeve. Used full wall thickness in calculation. Could save it, and away we go. And we could run that same report. But the other thing I wanted to bring out is, remember I said I'm going to include the longitudinal bending stress into calculation? Well, we could also calculate those under this module right here, design and stress analysis. So we can consider, now if you want to make this steady, just double click here, click here. I could use bending stress in calculation. I could use the I could use the hoop and longitudinal stress. I could use internal pressure if I wanted to. I could use maximum allowable pipe span length, and then also restrain pipeline stress analysis. So I have multiple ways also to calculate, and also I have the capability to calculate it on and off in these calculations. So in this one, I have the same thing. I could bring this up. I have the same capability and run it the way I want, which is nice. I'm going to shut this down, but just to let you see what the capabilities are on this, and then run the various calculations. I'm going to come over here to this one right here. And this is span max, and it's the same thing. I'm going to shut this off so I can show you what's going on here. And it's the same thing with, and all of these, if you notice they're in green, these were automatically put in by me just touching this in the hierarchy or lighting up the pipeline. And it automatically imports the data because the data was already imported into the system. And that's how you know where the data came from. That this came from the hierarchy. And this is located over here. And it's, you notice this way you don't get messed up with data and get it wrong because it makes all these calculations consistent. And where do we find them? I got AC calculations. I bought above ground, I'm sorry, accidental release, pipeline crossings. And I got wheel load crossings, R string calculations, etc. And these are the nice things about this, the bending stress and so on and so forth. I'd like to thank you very much. If there's any questions, you could always create a support ticket. You could request new product information, license keys, report a bug, engineering technical questions, request governance information, feature requests. In addition to that, we have this right here, a hub bot, and we got frequently asked questions. We also have user guides, talk to a representative, learning library, training schedules, and support. I'd like to thank you for your time, and if there's any questions on track load analysis and temporary crossings, feel free to call. Thank you.